Hi, and welcome to a new 3DEqualizer4 tutorial. Today, we're exploring the exciting new features of 3DE4 Release 8.0. Let's dive into the GUI improvements, starting with the updated options for the overlay grid. These changes are designed to enhance your precision and efficiency in tracking. As you can see, we've loaded a shot of an actor wearing a suit with markers attached to it. You might recognize him from our previous Rotomation tutorial. Tracking such markers can be challenging, especially when they regularly become obscured by the actor's arms and legs. For example, in our case, point 24 is invisible between frames 69 to 109. For a flawless rotomation of the actor's legs, however, it's helpful to at least guess the tracking of point 24 in these frames. For this purpose, we've added a few new features to 3DE4's overlay grid. Let's activate the grid through manual tracking controls, View, Overlay Grid, Show Grid. This grid acts as a visual reference when estimating the position of occluded tracking features. To improve its functionality, we've added the option of displaying a circle. In addition to that, a secondary aim point can be defined. Let's do that real quick. Select the aim point, in our case, that's point 25. Then choose Set Aim Point from the Overlay Grid menu. The menu label now indicates that point 25 is the current aim point. If we now select point 24 again, the overlay grid is always automatically rotated so that points 24 and 25 are located on one axis of the grid. Let's scale down the grid a bit so that the circle goes directly through point 25. When we scrub through the sequence, we can clearly see that the leg of the actor doesn't move in sync with the grid between frames 69 to 109. Point 24 seems to be quite off, especially in frame 86. Let's fix this. Click-drag point 24 to a position on the screen where the actor's leg better matches the orientation of the grid, and the circle still goes through point 25. That seems to be much better. However, frames 76 and 97 also need a makeover. Okay, that looks much better overall. It's still not perfect, but I think you get the idea. This technique can be used not only for the limbs of actors, but also for those classic sword and especially arrow match moves. It showcases the power of 3DE4 Release 8.0's new features. Let's continue with a closer look at the latest updates to 3DE's Rotomation editor. If you're not yet familiar with how to use the Rotomation editor, I recommend watching our dedicated tutorial on that subject first. With our Rotomation project still loaded, you'll notice we've tracked roughly 25 points on the actor's body. In addition, his movement in 3D space has already been reconstructed with the help of Rotomation editor as well. we've introduced an additional option in the menu labeled Show Alternative Solves. This new feature allows you to display solves for selected points only, rather than for all points. It's a significant improvement for understanding complex scenes. Upon enabling the display of mocap trajectories, you'll now see these trajectories consist of red and green sections. Green sections indicate frames with 2 possible solves, while red sections denote there is only one solve, typically because the parent bone is too short in those frames. We've also added new features for scaling the currently selected bone up or down. Watch how the color scheme of the mocap trajectory updates accordingly to reflect these changes. In the curve editing section of the Rotomation editor, we've added some convenient features. Patch CVs helps remove bumps from the curve, enhancing the smoothness of your animations. Shift Curve allows you to move the curve back and forth along the timeline in case some frames are being added to a shot. Additionally, we've introduced a feature for filtering multiple child points at once, streamlining the editing process for complex rotomations. To better support the visualization of rotomations, we've added an aim constraint for 3D models. Let's try that out. First, create a cube. Then activate its snap to point feature and select point 9. Set the constraint mode to aim y-axis and select point 10. To make the cube resemble a lower leg, we'll make it longer and a bit narrower. To create such bone 3D models more quickly, duplicate the cube we just created. Select 2 points and the duplicated cube. Then use the attach 3D model to point pair script. This script will automatically activate the cube's snap to point and aim y-axis feature and assign the selected points to it. Running the script again will swap both points. Let's quickly create 2 additional cubes for his upper legs as well. Thanks to the newly attached cubes, visualizing the actor's movement has now become significantly clearer, allowing for a much more intuitive understanding of his motion within 3D space. And that concludes our overview of the latest enhancements to the Rotomation editor in 3DEqualizer4 Release 8.0. These updates are designed to streamline your workflow, making the process of Rotomation more intuitive and efficient than ever before. Next up, let's focus on lens distortion, specifically highlighting our new tool for estimating focus changes. We have a photo booth shot featuring a head model and some background elements. The focus transitions from close-up to infinity. You'll notice significant changes in the appearance of some background lights due to these focus shifts, resulting in classic bokeh effects. Our latest tool is designed to measure and display these bokeh changes efficiently while tracking one of the lights. To add this tool into 3DEqualizer, select Config, Add Horizontal Pane, Display Marker Size. This pane predominantly features a curve area. Let's enlarge it for clarity. Now, let's track one of the background lights using 3DE's marker tracking. Create a new point, adjust the tracking boxes, and set the tracking mode to marker. Upon initiating tracking, 2 curves, one green, one red, are generated in real time within our tool. The green curve tracks the marker's maximum height in pixels, and the red curve its maximum width, giving us an accurate depiction of marker size throughout the shot. Tracking another point, this time in the foreground, shows that individual marker size curves are remembered when switching between points. The curves differ significantly because the distance of each marker from the camera is different, of course. Zooming into the curves reveals that even minor focus shifts affect the marker size. Flat curves indicate stable focus, while changes in the curve denote focus adjustments, allowing us to precisely identify when focus changes start or end. But can these curves directly inform us about the absolute focus curve? Examining frames 750 and 900, we see the green curve values are similar, but the red curve differs. Zooming out, it's clear these frames have been shot at different focus settings. This discrepancy stems from the light's positioning closer to the camera, in the midground rather than the background. The frames around 750 have been shot at infinity, whereas at 900, a different focus closer to the camera has been used. Let's look at another shot, where the camera pans with changing focus against city lights. Again, tracking one of these lights demonstrates how marker size curves indicate focus changes. Since the light is far in the background, there is now a reversed, but more or less direct relationship between the marker size curves and the actual focus curve. Estimating an absolute focus curve from marker size curves is complex, influenced by various factors such as light pattern size, lens characteristics, and aperture. Also, camera movement towards or away from markers affects the analysis. This tool, however, excels in identifying start and end points of camera focus changes and is a practical addition to 3DEqualizer's toolset for handling dynamic lens distortion without grid shots. It's especially useful for creating keyframes for the Adjust Curve Vertices script, pinpointing focus curve turning points. Now let's look at another advanced lens distortion feature, introduced in 3DEqualizer4 Release 8.0, the capability to import frame-by-frame lens distortion data from STMaps. This functionality addresses a common challenge within the VFX industry: the storage-intensive and inflexible nature of distortion data provided by some third-party tools as sequences of OpenEXR STMap image files. Traditionally, these image sequences, while effective, consume significant storage space and offer limited flexibility in post-production workflows. As you're aware, 3DE's approach is significantly more efficient, as it describes lens distortion using just a few floating point parameters. This method is not only more storage efficient, but also provides the flexibility to easily optimize these parameters at a later time as needed throughout the post-production process. To bridge the gap between 3DE and third-party tools, especially in collaborative environments where multiple companies may be working on the same project, we've introduced a new import feature. It converts a sequence of OpenEXR STMap images into dynamic distortion parameters of a lens object within 3DE4. A common workflow looks like this. Firstly, import the footage for your project. For demonstration purposes, we'll use the head focus footage available in our tutorial dataset. As you might remember from previous tutorials, it shows the model of a head which is filmed by a locked-off camera with an anamorphic lens. Due to a rack focus, pronounced lens breathing artifacts are visible. Once the footage is imported, navigate to 3DE, File, Import, Import Distortion from STMap Sequence to initiate the new tool. A dialog window will appear, prompting you to browse and select the appropriate STMap sequence that matches your imported footage. When configuring the import settings, you'll encounter several options. The Map option menu allows you to choose how the footage's field of view should be mapped to the OpenEXR files, with the default setting typically being the most suitable. The STMap Contains option menu lets you specify whether the STMap files contain undistort or redistort data. Since we are working with undistort STMap files in this example, we'll leave the setting on undistort data. You'll also need to decide whether to import the distortion data into a new or an existing lens object through the Target option. Next, select the lens distortion model suitable for the conversion. For our example, we select Anamorphic Standard Degree 4. The Import option menu then allows you to choose between importing distortion data on a frame-by-frame basis, creating a lens with dynamic distortion, or importing just static distortion from the first STMap. Additional details such as the pixel aspect ratio of the footage and any potential rescale values for pre-scaled footage are also required. If the footage has been pre-scaled, ensure to select one of the rescaled distortion models. Last but not least, the Calc Lens Center Offset toggle buttons allow you to decide if static lens center offset parameters should be calculated during the import process. Finally, click Import to start the conversion procedure. 3DE will now process each STMap file, analyzing and calculating a set of distortion parameters accordingly. This process can take some time, depending on the resolution and number of frames involved. Upon completion, an average deviation value, indicating the accuracy of the import, is displayed. In our case, an average deviation of 1.2 pixels is achieved, which is quite a good result. The newly created lens object is set to dynamic distortion, reflecting the previously specified requirements. By scrubbing through the shot and examining the individual distortion parameters, it's evident that all parameters are animated, with detailed individual animation curves and a keyframe on every frame. Conducting a quick visual quality check by stabilizing the shot and comparing views with and without distortion compensation reveals the high quality of the conversion procedure. Well, guess which software conjured up these STMap files in the first place? This comprehensive approach to importing lens distortion data from STMap image sequences into 3DE helps to streamline the post-production process significantly. It's a testament to the software's commitment to providing advanced, user-friendly features for the visual effects community. In recent years, it has come to our attention that specialized lens or camera equipment used in the industry can pose challenges for 3D tracking software like 3DE. So, we have introduced two new lens distortion models in Release 8.0 to address these issues. We have a project here that contains two shots that are quite similar to each other. As demonstrated, the camera executes a circular panning motion while capturing a green screen with markers. Approximately 8 survey points are tracked, yielding an average deviation of about 0.98 pixels. Turning our attention to the second shot, it is virtually identical to the first, tracking the same survey points with the camera moving in a nearly identical manner. However, the deviation in this shot reaches around 2 pixels. Moreover, the shape of the deviation curve suggests some unusual systematic fluctuations. The question arises, why does this occur? Both shots were filmed using the same camera and lens. However, for the second shot, we activated the lens stabilizer feature. What does a stabilizer do exactly? A stabilizer uses gyroscope sensors to measure camera movements, identifying any undesired jittering or shaking. To counteract these movements, either the image sensor inside the camera or an element within the lens is moved in the opposite direction. Sometimes, both sensor and lens elements are adjusted. Unfortunately, this is problematic for 3D tracking software because it alters the geometry of the image, a fact our example clearly illustrates. To mitigate these effects, we have introduced a new radial and an anamorphic distortion model. These models are somewhat based on pre-existing models, but include 2 additional stabilizer parameters for the X and Y axes. Modifying these parameters significantly impacts the image, as you can observe. Their effect somehow can be compared to that of our standard UV lens decentering parameters, though they are not exactly the same. Before utilizing these new parameters, let's examine the match move results closely. At first glance, using lineup controls, the results seem satisfactory. However, a closer inspection reveals significant shifting issues. Due to the dynamic nature of these stabilizer lenses, it becomes necessary to animate the stabilizer XY parameters. This is achieved using the good old Adjust Curve Vertices script. First, we use 3DE's Animate Distortion tool to mark control vertices at key turning points in the deviation curve. These points suggest changes in the movement direction of the camera's sensor and/or lens elements. Alternatively, examining the footage directly may help identify moments of directional change in the camera. After creating CVs on the stabilizer curves, we incorporate the parameter adjustment window into 3DE's panel layout. Select all CVs and add them to the adjustment list. Adjusting around 40 parameters, as in this scenario, may be time-consuming. In our case, the process was concluded after approximately 5 minutes. As evident, the deviations significantly reduced to 1.24 pixels, underscoring the effectiveness of these new parameters in enhancing the situation. Upon accepting the adjustment results, the stabilizer XY curves are updated to display systematic patterns, as anticipated. After calculating the project, the deviation curve still presents some systematic errors, but the overall improvement is evident. A quick visual inspection confirms that the match move quality has notably improved. It's worth acknowledging that these stabilizers can have unpredictable effects, and in scenarios of high-frequency camera jitters, they may induce excessive vibration. Reviewing the stabilizer curves suggests that adding more control vertices could allow for a more detailed reconstruction. Wouldn't it be nice if we could simply create more CVs? Maybe even on every single frame, for example. It would. So, let's do it. We could theoretically generate hundreds of control vertices and use Adjust Curve Vertices to optimize all of them at once. However, this process would probably take almost forever. So, what are we talking about? We're talking about a new script designed to optimize the CVs of individual frames. Let's test it with our stabilizer project. Upon reloading the original file, we find the deviation back at 2.1 pixels, with no control vertices present on either stabilizer curve. Given the lens's static distortion, we employ 3DEqualizer's Animate Distortion tool to create a single CV. This sets the lens to dynamic distortion and initiates a focus ramp-up curve. We then select Curve Editor, Edit Resample Curves, which facilitates the creation of uniformly spaced CVs across all active curves within the curve editor. Initially, we generate a CV for every 5th frame while removing any original CVs. With a single button press, approximately 130 CVs are generated. Next, we turn our attention to our new precious. Navigate to Curve Editor, Calc, Optimize CVs. A dialog box appears, offering various options. It includes a list for selecting parameters to include in the optimization. Additional options cover potential parameter and frame ranges. To commence the optimization, simply click on Optimize CVs. The process is notably swift, especially when compared to the lengthy duration of previous parameter adjustment procedures. The increased CV count significantly enhances the detail of both stabilizer curves. In addition to that, the deviation reduces to 1.08 pixels, though some systematic issues remain evident. We proceed to verify the match move as before. The reconstruction shows improvement, yet some irregularities persist. Given the rapid calculation, let's integrate more parameters. We select the degree 2 distortion curve for resampling, followed by another run of optimized CVs. Introducing a third parameter slightly extends the processing time, yet it remains impressively quick. The deviation further decreases to 1.03 pixels. The distortion curve exhibits some nice systematic patterns. Let's incorporate both degree 2 UV parameters. To expedite the process, we enable multi-threading, leveraging the computing power of the local machine. However, with a low number of parameters, the impact is relatively modest. The deviation is reduced to 0.93 pixels, though some systematic artifacts are still visible. Upon examining the distortion curves, we observe a decline in stabilizer curve quality compared to earlier results. This likely results from the similar nature of stabilizer and UV curves, where adding more parameters provides the system with additional means to compensate, potentially leading to more degrees of freedom for cheating. A visual match move check reveals little improvement. When we compare the deviation of both shots, we notice that with 0.93 pixels, at least we're now in the same area, although the systematic bumps of the shot with activated stabilizer are still much more pronounced. Nevertheless, these new distortion models will enhance the quality of such stabilized shots. To complete lens distortion topics for this video, let's try out our new Optimize CVs tool with a different shot. Here is a prepared head focus project, familiar from previous tutorials, showcasing a rack focus with a virtually stationary camera equipped with an anamorphic lens. Some distortion parameters are pre-animated, resulting in a deviation of approximately 1.1 pixels. A preliminary visual inspection reveals minor misalignments between the survey and 2D tracking. Employing our new method, we select all distortion curves excluding lens rotation and resample them at a rate of 5 frames, amassing an impressive 580 CVs. We then run optimized CVs in multi-threading mode. As anticipated, processing this extensive array of parameters takes time. Well, look at that. Surprisingly, the final calculation significantly reduces the deviation to 0.2 pixels, which is roughly 5 times lower than the initial deviation. However, a closer look at the distortion curves reveals they have absorbed considerable noise. This noise becomes apparent upon visual inspection. Yet achieving a deviation of 0.2 pixels for a survey project at full HD resolution is outstanding. To mitigate this noise, we opt to filter the distortion curves using the Gauss filter with a cutoff setting of 15. After a recalculation, the deviation only slightly increases to 0.2085 pixels, a result that is quite surprising. The final result now looks very good. So, will this be the new wonder weapon in match move land? Not so fast. There are several drawbacks that must be considered. Primarily, this technique is applicable only with a substantial number of survey points, ideally limited to survey points only projects. Simultaneously, adjusting static parameters like focal length or rolling shutter is not possible. Attempting to optimize focal length concurrently transforms it into a zooming project. We recommend reducing a project's deviation using traditional methods first, before applying this new technique. Finally, this technology might inadvertently shift problems within a project. For instance, if poor 2D tracking or survey data is present, this technique may adjust distortion to yield seemingly accurate deviation values, potentially compromising other frame areas with fewer tracking points. Hence, this approach is unlikely to obviate the need for precise 2D tracking or survey in the near future. Despite these considerations, we think this technology is still super cool though. Let's continue with exploring 3DE's enhanced data exchange capabilities through a new file format called 3DE ASCII. This new format is particularly exciting as it allows for the export of entire projects via editable XML files. This means these XML files can be created outside of 3DEqualizer using in-house software tools. Additionally, the 3DE ASCII files generated by 3DE Release 8.0 can be imported back into legacy versions, such as Release 6, effectively allowing for backward compatibility. Let's start with a complex example involving a motion capture project. In this project, we're dealing with 3 cameras, 2 point groups, and 3 individual lenses. Each point group is tracked across all cameras. And the scene includes an animated mesh driven by approximately 100 mocap points. To manage this new feature, navigate to the 3DE ASCII menu. Here, you'll find scripts for exporting, importing, and merging these files. First, we'll export our current mocap project to a new ASCII file. When you initiate the export, a new requester window will appear, providing several options. You can define how much of the current project you want to include in the export file. We'll select the option Entire Project to ensure all data is captured. After some time, the file will be successfully exported. Now, let's import this file back into 3DE. Navigate to 3DE ASCII Import and select the previously exported 3DE ASCII file. The project will be purged, and all data present in the 3DE ASCII file will be imported. Let's take a quick look at what has been imported. As you can see, all cameras with their lenses, point groups, 2D tracking, and even the animated mesh have been successfully brought back into 3DE. Finally, let's run a calculation on the project to see if everything works correctly. Looks good. Both point groups show the correct deviations for the main camera. Let's now explore importing a project into Release 6 using the 3DE ASCII format. For those of you looking for the necessary scripts, both import and export scripts for 3DE ASCII can be found in the ScriptDB section of our website. Let's begin by starting the import script and selecting our previously exported 3D ASCII file. After some time, the data previously exported from Release 8 have been successfully imported into Release 6. Let's check the results. Everything appears to be in order, including the animated mesh, which has been fully restored. Upon calculating the project, we see familiar average deviation values, which confirms the success of our import. Now, let's head back to the future and try merging two different projects. We'll start by loading the mocap project we've been working with. Navigate to 3DE ASCII Merge, and a new window will appear. This window won't block 3D's interface, allowing it to remain open at all times. Select another 3DE ASCII file that we exported previously. Once loaded, its contents will be displayed within the window, mirroring exactly what you would see in 3DE's object browser. Objects that can be merged into the current project are indicated in yellow. There are several options to configure the merge process. Automatic import. We opt for import selection only, since we wish to import each object separately in subsequent steps. Camera point group. Decide whether data associated with the camera point group should be merged with the existing one or not. Points. Determine how and if the imported points should be merged with existing points. 2D tracks. Choose where the 2D tracking curves of the imported points should be placed. Let's begin the merge by bringing in a single additional camera. Voila! Here we go. The project's object browser shows that this new camera isn't linked to any lens object. We'll fix this by merging in the corresponding lens and then linking the newly imported camera to this lens. Next, let's integrate a 3D model. This model will be merged into the currently active camera point group. Everything checks out here. Finally, we're merging all points from the camera point group into the existing group. We'll add a prefix to the point names during this merge, making it easier to identify the newly imported points later on. This step concludes successfully. After recalculating the project, we can confirm that we have successfully merged the head focus shot into the existing project. Let's repeat the previous merge process, but this time in full auto mode. First, load the mocap project and open the head focus 3DE ASCII file. Set the automatic import to Import Upstream Dependencies. This setting automatically links cameras to their lenses, simplifying the import process. Then, select the camera, all points, the 3D model, and the lens, and finally hit Merge. As you can see, all assets have been imported in one step. Calculating the project once more shows the same successful result as before. Now, let's explore how different parts of a project, perhaps created by multiple artists, can be seamlessly montaged together. Let's load the mocap project again and delete one of the witness cameras, which includes all of its 2D tracking data. Reopen the merge script and import the mocap project. This time enabling the manual import mode. We also allow newly imported points to be merged with existing points of the same name and enable 2D tracks to be merged into the current camera, giving us more control over which of the original tracks should be copied over to the project. Here's how we proceed. First, select the previously deleted camera and merge it back into the project. Then, link the camera to its correct lens again. Next, select all camera point group points and decide which of the original 2D tracking curves should be imported. As you can see, the previously deleted 2D tracks have reappeared and are merged with the original points, avoiding any duplicate ones. As a final step, let's bring back the mocap points. Make the imported camera and the mocap point group the current ones. Then, select all mocap points and merge them back into the project. Upon recalculating the project, we see no difference in both deviations, which means that merging back one of the witness cameras together with its associated 2D tracking curves went well. That concludes our walkthrough on utilizing the 3DE ASCII file format for efficient data exchange and project merging in 3DEqualizer. We hope these tools empower you to streamline your workflow and collaborate effectively across different versions and projects. Let's explore another new data exchange feature of 3D4 Release 8.0, the ability to import and export assets via Universal Scene Description (USD) files. We'll start with the familiar mocap project used in the previous section of this video. Similar to 3D's legacy Alembic I/O features, there's a dedicated export project script to create new USD files and an import script to import specific assets into 3DE. First, let's export the current project. Select Export Project USD. A new window will appear, offering options similar to the Alembic export script. We'll rename the USD root node to TDE mocap. Select a new file name and click OK to create our new USD file. USD files generated by 3DE contain some additional custom attributes, such as 3D camera and object motion data, 3D point clouds, 2D tracking curves, lens distortion data, and more. Now let's import this data back into 3DE. Navigate to File, Import, Import USD. And a new window will appear. Again, this window closely resembles the Alembic import window. The window doesn't block 3DE's user interface, so it can remain open at all times. First, let's import the previously exported USD file. Clicking Expand All will display all the file's items. Each entry shows the object's name and its associated 3DE object type. Next, let's examine the Options menu. we want to import the mocap project alongside the existing camera, so let's configure some options. We'll disable Replace Already Existing Points to avoid overwriting any old points. We'll also enable Add New Camera and Lens automatically to prevent overwriting the current camera with the one stored in the USD file. Finally, we'll select the camera, all camera points, the mocap point group and its points, as well as the animated mesh. Pressing Import will bring in all the assets. Let's take a closer look. The animated mesh needs some makeup. But overall, everything looks good. The 3D camera, its tracking points, lens, and the mocap point group, along with its points, have been successfully imported. The previous camera remains unaffected as well. As you can see, USD files exported by 3DE can easily be imported back into the application. But what about files created using other tools? Let's test this by loading a USD file that was created externally. This file contains a camera and a LiDAR scan, along with some group nodes. When importing external USD files, items that are clearly identified appear in green. Those that can be imported but not assigned a specific object type are shown in yellow. Items displayed in white cannot be imported at all. If you attempt to import a yellow item, 3DE will suggest an object type, which you will need to confirm. Let's first import the LiDAR scan, which has been provided by Vertices VFX. Finally, we'll select the camera and import it as well. Overall, the new USD import and export features make asset management more flexible and compatible with other tools. This concludes the overview of the new data exchange features found in 3DEqualizer4 Release 8.0. This video is coming to an end now, but before we wrap up, there's one more thing to show. We've added the ability to create 3D models from 2D masks. These 3D models, called blocking objects in 3DE, can be used in third-party tools as holdout mask objects, allowing CGI to travel behind certain foreground live-action elements. Here, you see a shot where the camera moves from right to left, capturing an open field. In the foreground, there are some concrete construction elements. Using auto-tracking masks, we'll create blocking objects for both concrete structures. Let's switch to the auto-tracking controls. First, we create a spline mask to define the contour of the left-hand concrete tube. The dark auto-tracking mask can obscure the contour, so we disable its display temporarily. We select all CVs and set them to linear. Now let's define the contour of the concrete tube as precisely as possible. As usual in 3DE, new CVs can be created by holding down the Control key while clicking with the left mouse button. For the round parts of the tube, we set 2 of the CVs back to spline mode. Our first mask is done. Red markings in the timeline show the keyframes of all currently selected masks. Please note that the first frame is always a keyframe. If we scrub through the frames, we notice our mask is heavily distorted in interpolated frames. This is because we started editing our mask at frame 70. To correct this, we copy our mask from frame 70 to frame 1 through Edit, Synchronize Keyframes. Brilliant, it looks much better. Now, we want to disable our mask in the first 30 frames since the concrete tube isn't visible at the beginning of the shot. To do this, we go to frame 1 and select Edit Toggle Visibility State. As you can see, our mask is now disabled from frame 1 to frame 69. Next, we create 2 additional keyframes towards the beginning and end of the shot. To move our mask, we select all CVs and hold down the Shift key while click-dragging one of the CVs with the left mouse button. It seems the mask is slightly too small for the concrete tube, so let's scale it up a bit. We introduced a new feature for transforming selected CVs. First, let's dial down the scale strength. Then, we click the Scale Plus button a few times. The nearby Rot buttons do exactly what you'd expect. Finally, let's adjust the CVs to accurately describe the contour of the concrete tube in that frame. We repeat this step for another frame. To achieve a plausible overall motion of the mask, we modify the keyframe in frame 1. And add an additional keyframe to the last frame of the shot. That looks good. Now we're ready to test 3DE's new blocking feature for the first time. Within the 3D orientation controls, select 3D Models, Create Blocking Objects. A new window opens, showing several options. Note, for this feature to work properly, we need a good 3D solve with properly adjusted lens distortion. The upper half contains settings for the number of frames included in the calculation and the resolution of the source masks. The lower half has settings to control the calculation outcome directly. For now, we stick with the default settings, meaning only keyframed mask frames are used. To start the calculation, press Create Blocks. After a moment, 2 new red 3D models appear, but they don't look correct at all. Let's check this in lineup controls. Scrubbing through the timeline, we see the concrete tube is covered by the blocking object, but in many frames, the 3D model is too large and extends beyond the actual contour of the tube. Let's examine the situation closely, focusing on the mask keyframes in frames 57, 70, and 105. The blocking object fits well in these keyframes. Obviously, we need to define a few more masks to cut off unwanted parts of the blocking object in order to achieve a better result. Let's concentrate on the separate, triangular-shaped part for now. We need to find a frame where it is visible within the field of view, but separated from the good part of the blocking object. Frame 101 seems suitable, so let's quickly add another mask keyframe. Switching back to orientation controls, we delete the previous 3D models and rerun the calculation. Since we added another mask keyframe, we increase the source masks to be used setting to 5. That looks different already. The separate portion of the blocking object is much smaller. In lineup controls, Frame 101 shows a better result. To remove the remaining triangular-shaped blocking object, we can either create another mask or simply select and delete it in orientation controls. However, for demonstration purposes, we add another keyframe in frame 91. After another run of the procedure, the separate blocking object has vanished. This demonstrates the common workflow technique for situations where you can't create a mask in every frame. In lineup controls, scrub through the footage to identify areas where the blocking object is too large. In our example, the beginning and end of the shot, around frames 30 and 125, clearly exhibit these issues. Add more mask keyframes in those areas. And rerun the calculation, carving off more material from the blocking object. Alternatively, you can allow 3DE to use interpolated mask frames in the calculation, but this might introduce false masks and lead to poor quality blocking objects. Another solution is to import an image mask sequence created externally. Let's explore this option now. We have an image-based mask sequence prepared that covers the right-hand side concrete block. In the attribute editor, disable all existing spline masks and enable the image mask feature. A matching mask sequence has already been imported. Since the imported mask appears inverted, enable the Invert Image Mask option. Now the concrete block is masked out in every frame. Moving back to orientation controls, let's give this a try. To include all possible frames in the calculation, disable the Use Spline Mask Keyframes Only option and set source masks to be used to the maximum possible frames of 130. Chewing through 130 frames takes some time. The result is interesting. The contour of the concrete block is properly reconstructed. Even the hole in the middle fits well. Now, let's address the elephant in the room. The blocking objects look good from the camera's point of view, but don't match their expected shape when viewed from a different perspective. This is because the camera's perspective is limited in terms of parallax, only showing the concrete elements from the front. There are two ways to improve this. First, there is a special option which estimates how much of a blocking object can be cut off after the regular calculation. Let's try this quickly. Concentrating on the left-hand side blocking object, we enable spline masks again and switch off image-based masks in the attribute editor. In orientation controls, we disable line rendering and change the color of the previous blocking object. Finally, we run the calculation again, while enabling option Limit 3D Models in Z Depth. This additional calculation step takes extra time, so enable it only after the blocking object has been fine-tuned. The result looks pretty good, as the reconstructed shape is closer to the real shape of the concrete tube. The second method for reconstructing more precise shapes of such blocking objects is simply by introducing more parallax. For our example, we add a single reference frame showing both concrete elements from above from a different point of view. 2 spline masks have already been added. And the reference camera has been included in the solve. For the final run of 3DE's Create Blocking Objects feature, ensure all cameras and 131 frames are included in the calculation. Set quality to 1.0 for more detail in the blocking objects, and disable the Limit 3D Models option. Well, look at that! Just by adding a single reference frame, we create convincing 3D models. The final result looks good in lineup controls. If the blocking objects have too many faces after setting quality to 1.0, use 3DE4's new Decimate 3D Model feature to make it low poly. Let's try this. Select one of the blocking objects. Then run the script Decimate 3D Model. A new window appears, allowing you to set the decimation factor and destination 3D model. In our example, we save the result in proxy slot number 1 of the same 3D model and set the decimation factor to 0.1. Switching between proxy slots shows the original model is not lost. This feature can also be very helpful when working with huge LiDAR scans, allowing regular user interface work with stripped-down versions while maintaining good GUI performance. For extracting 3D survey data in F5 or F6, you can temporarily switch back to the high-definition version. Finally, let's put some CGI elements behind those blocking objects to see if they fulfill their purpose properly. We project the footage on the blocking objects, create 2 narrow boxes, and place them in the background. This brings us to the end of this video. We hope you found it enjoyable and informative. 3DEqualizer4 Release 8.0 is now available to all customers, packed with new features and enhancements. For more details, visit the DevBlog section on our website. Thank you for watching, and see you in the next one. Goodbye, and take care.